Welcome back to the next video, everybody. Today we're going to look at Langland's tunnel and the minimal level. So we're going to explain some details about the Langland's tunnel portion of the proof of semi-stable modularity, which were left out during chapter 6, but which will be used in the proof of the minimal case of R equals T in chapter 14. We're going to have to prove a minimality result about the level, basically. So given a semi-stable elliptic curve E over Q, we have to make sure that rho bar E3, the mod 3 representation attached to E, can be chosen to be of minimal type. So we want minimal square-free level. Weight 2 trivial character. All right. In what follows, just recall, for example, that let's see, so N of rho, the conductor of rho, is the prime to L part of the conductor of E if rho is the L-adic representation attached to E. Also recall that N of rho bar always divides N of rho. So this is a carryall or Livni result. And then also remember that because N of rho is the prime to L part of NE, 3 will definitely not divide the conductor of rho bar E3. So this is all stuff I talked about in chapter 1 of my notes. It's all typed up there. Okay, so here's the main results of the day. Let E over Q be an elliptic curve such that rho bar 3, which is just rho bar E3, shorthand, is irreducible. We know by proposition 1 that rho bar 3 is surjective. Remember, irreducible is the same thing as surjective in this setup. So theorem 6, under the above setup with the above notation, rho bar 3 is actually modular of type. The level will be the conductor of rho bar 3, weight 2 trivial character over Q bar 3 if rho bar 3 is flat at 3, and if not, then you have to multiply the level by 3. Okay, so let's prove this. This is difficult, actually. So step 1, we already showed in the Langland's tunnel chapter 6, that rho bar 3 is modular. And by a result in the Sayre conjecture paper in section 5.3, the conductor of rho, which is psi composed rho bar 3 from step 2 of chapter 6, so this is when we embedded into the GL2 of that number field Z adjoint root -2. The conductor there is 3 to the m times the conductor of rho bar 3 squared for some m non-negative. And you can check using essentially just the definition of the Artin conductor that in the case rho bar I3 is isomorphic to the mod 3 cyclotomic character direct some trivial character, m must be 1. And that in all other cases, m is bigger than 1. So if you translate what Langland's tunnel actually says into the language of this chapter using the Sayre result, you find that rho is modular of type the conductor of rho, 1, character that rho over Z adjoint root -2, meaning there's a cuspidal Z adjoint root -2 eigenform f of level the conductor of rho of weight 1 and character determinant of rho such that rho is isomorphic to rho bar f, or to rho f, where rho f from GQ to GL2C is the representation associated to f via Deligne Sayre. All right, that the conductor matches the level, by the way, is actually hard that you get to get the conductor here. That follows from Carryall's hard theorem, which I think I cover in chapter 20 of my notes much later. Okay, so we're basically modular of weight 1 and the determinant is the character. So we want to do better than that. We want to know that rho bar 3 is actually modular of type the conductor of rho 3 squared, comma the k that Sayre's conjecture prescribes, comma trivial character over f bar 3. We know it's actually modular of type conductor of rho 3 squared, comma k over f bar 3 for some k and n by theorem 2.1 in Ribot's level lowering theorem paper. And the case p is bigger than 2, which is the only case we need because we're working in the case p equals 3. There are unpublished proofs that work for all p, though. Okay, so step 2 allows me to conclude that rho bar 3 is modular of type n of, so conductor of rho bar 3 squared, comma k, comma 1 over f bar 3 for some k at least 1. Okay, I actually don't want just some integer k here, though. I want the k from Sayre's conjecture. If you want that result from step 2, this will be what I call step 3. You just look at theorem 3.5 in Edith Sovin's book on Sayre's conjecture. Okay, an overview of the major steps of the proof can be found in Cornell, Silverman, Stevens, page 232. And Taylor gives a relatively simple proof on page 233 of CSS that only applies to rho bar 3 by appealing to differentials and Mazur's results, Mazur's part of Ribot's theorem from a couple of videos ago. Okay, so we won't go through any of that, but so step 4 is where most of the work goes. Now I know that rho bar 3 is modular of type n of rho 3 squared, comma the k from Sayre's conjecture, trivial character over f bar 3. I would like to now reduce down to the case where this k can be replaced by 2 and where I can look at modularity over Q bar 3 if rho bar 3 is flat. And if I'm not flat at 3, I will have to scale the level n of rho bar 3 squared by 3. All right, so a generalized version of information we looked at in chapter 3, which was the modular curves, modular forms, L functions chapter, shows that cusp forms of type n2 1 over k, where k is a field of characteristic 0, correspond via what we call the Kodaira-Spencer isomorphism to differential forms on the modular curve x0 n over k, so the k model, i.e. to sections of the sheaf of differentials omega 1 on x0 n of k. And this isomorphism is compatible with the action of the Hecke operators. So we talked about this in a special case in chapter 3, basically when k was q, okay, or c. So let's let n equal the conductor of rho bar 3 squared if rho bar 3 is flat at 3, and 3 times that otherwise. What we have to do is we have to show that there's a non-zero differential form omega on a q bar 3 model of x0 n, which is a Hecke eigenform and whose Galois representation, which we'll call rho sub omega from GQ to GL2 of f bar 3, is isomorphic to rho bar 3. And this is where, if you remember at the beginning of this chapter, I gave you something called Carriol's lemma. We're going to require a version of that to do this. The hard part, though, it turns out, is constructing this eigenform over f bar 3 first, and then it follows immediately from some standard commutative algebra arguments using Gross's book, chapter 9, for example, that this construction will lift to an eigenform over q bar 3 with the required properties. So as a matter of fact, I just have to produce this non-zero differential, this eigenform over f bar 3, instead of over q bar 3 like I'm claiming I want. So how do you do this? Well, let's look at the case rho bar 3 is flat at 3 first. By the discussion at the beginning of subsection 2 of this chapter, 3 and n are coprime, and our representation is associated to a cusp eigenform f of type n2 over f bar 3. Okay, so this was something that we talked about already. We wish to find a differential form omega on an f bar 3 model of x0 n, which is a Hecke eigenform with the same eigenvalues as f. The problem is you can't, in general, in this setup, view f as a section of the sheaf, the second tensor power of omega, which is what you want to do according to the beginning subsection of this chapter on x0 n of f bar 3, and then just apply Kodaira-Spencer to get the eigenform you're after. The problem is, over f bar 3, the modular curve x0 n doesn't admit a universal family of generalized elliptic curves with level structure of type gamma 0 n. Okay, go back to the first video in chapter 7 on my playlist to see what I'm talking about here. Okay, in the material found in chapter 3, universal elliptic curves are used to build the so-called Kodaira-Spencer isomorphism in that special case, even in a far more concrete setting. So if we don't even have that here, then we can't hope to do things so easily. So there's a trick, though. So let's let n be bigger than 3 and coprime to 3. According to standard theory, you can view f as a section of the sheaf omega second tensor power on a smooth projective curve x over f bar 3 that does carry a universal family of generalized elliptic curves equipped with a point of order n and the trivialization of the n torsion. Okay, now the curve that I want to work with, which I'll call y, which is an f bar 3 model of the modular curve x0 of n, is actually a quotient of this group by an action of g, which is z mod nz cross times gl2 of z mod nz on x. Okay. And then f is what f turns out to be a g invariant section of the second tensor power of omega. So on that curve, you can apply Kodaira-Spencer then, because you have the universal family of generalized elliptic curves. That gives you a global differential form, which we'll call omega of f on x, though, which isn't what I want. I want something on y. But Kodaira-Spencer is functorial. So omega of f is still g invariant, all right? So I'd like to see that omega f is actually the pullback of some unique differential form, which I'll also call omega of f on y, and then I'll be done. Now, the uniqueness, if the existence happens, follows immediately from the separability of the morphism pi from x to y, okay? Because if you look in like Silverman 1, for example, you see that under that kind of setup, the pullback map on differential form should be injected. So now we need existence. Why does omega of f exist? This is a little bit tricky. I don't want to get into the details. It's dealt with nicely in Cornell, Silverman, Stevens, page 235. And basically, you rely heavily on observations about the Hecke operators, and you end up contradicting a fact that we haven't really used yet, as far as I know. But you use the fact that rho bar 3 isn't induced from the Galois group of Q adjoined root -3, which we proved a couple of videos ago in this chapter. Okay, so you get what you want at the end of the day. Okay, but that proof only works in the case rho bar 3 is flat at 3. If it's not flat at 3, this time x0 n over f bar 3 has two irreducible components, which are each isomorphic to the modular curve x0 at level conductor of rho bar 3 squared over f bar 3. And how do these irreducible components intersect? They intersect transversely at the supersingular point. So the points representing supersingular elliptic curves at this level. Okay, wow, mod 3. okay? And the sheaf of differentials on x0 of n over z3 is not locally free of rank 1 at the double points over f bar 3. And so it turns out that because of that, it becomes hard to work with. So what you do is you just proceed in similar spirit by instead analyzing the so-called dualizing sheaf of the sheaf of differentials on this x0 of n over z3 model. And this turns out to be locally free of rank 1. So some details can be found in Gross's book in proposition 9.3 to get the needed omega of f that we want. You can also see Maser-Ribbitt's two-dimensional representations in the arithmetic of modular curves for more information about the dualizing sheaf. And then you can just see CSS for more details on the argument. Okay, so step 5, what do we know now? We know now from step 4 that rho bar 3 can be assumed to be modular of type conductor of rho bar 3 squared, weight 2 character 1 over q bar 3, if rho bar 3 is flat at 3, and that we have to scale the level by 3 if not. What do we want to do now? We want to kill these squares off, okay? Otherwise, we're definitely not minimal square free level like we'll need, okay? So how do we do that? This is accomplished through a result that we had earlier in this chapter called Carriol's reductions. So we have 3 things going on here. We have Carriol's theorem, Carriol's lemma, and Carriol's reductions. So Carriol's reductions were a reduction of theorem 2, okay? Carriol's theorem is about local global compatibility, okay? And Carriol's lemma is about surjectivity of reduction maps. So you'll have to probably go back and rewatch the entirety of chapter 7 of my playlist to really understand a lot of this stuff, but that's okay. So to prove step 5, to finish, some minor background, let's let P be a prime and suppose that F with Fourier coefficients A sub n of F is a new form of some type nk epsilon over QP bar with K at least 2. Let's let rho F be the usual p-adic representation associated to F. So recall this is the unique representation unramified outside NP and such that for L not dividing NP and prime, rho of F for Frobenius sub L has trace A sub L of F. Okay, so these are the kind of the defining important properties of rho sub F. Okay, now there is, on the other hand, another representation pi sub F from GL2 of Z hat cross. So this is the pro-finite completion of Z tensor Q to GL of V, where V is an infinite dimensional QP bar vector space associated to F. We won't describe this here. It's talked a little bit about in CSS page 237, and also the CRG paper of Carriol talks about it. You know from standard theory like the tensor, you know from standard theory such as the tensor product theorem, I don't know how to say this, Maggioliditis. The tensor product theorem is a great reference for that. Also bumps automorphic forms and representations, chapter 3. That V is an irreducible representation, actually, and that you can break V down via a restricted tensor product into V sub L's in a nice way. And what are these V sub L's? They are irreducible admissible representations, pi sub FL from GL2 of QL to GL2 of VL. So you can kind of break this big kind of global representation down into local representations, one for each prime. And these representations are irreducible and admissible, so they're pretty nice. Results in the Carriol paper describe for primes L that aren't P, the restriction, rho FL of rho F to some decomposition group at L in terms of pi FL. So this is Carriol's big thing, this local global compatibility. It follows that n of rho bar F actually divides n. Okay, what was n? N was the level we started with. So you can always get n of rho bar F to divide n. And what's rho bar F here? Remember, it's the semi-simplification of the reduction of rho F mod P, okay? And we're assuming this is irreducible. Okay, so in CRG and the LCM paper, so the Livni and Carriol papers, the authors classify in terms of the pi FLs, the L's that aren't P that divide n over the conductor of rho bar F. So it's interesting to ask, like, all right, I know n of rho bar F divides n, but what are the primes that aren't P that are left over when I do this division? So Carriol and Livni have a famous paper or set of papers classifying these, okay? So the strategy is as follows. You know rho bar 3 is modular of type n21 over q bar 3 for some n that divides n of rho bar 3 squared. So let's let L be a prime that isn't 3, and we'll suppose that L squared divides n. It suffices to show that rho bar 3 is modular of type n prime 21 over q bar 3 for some n prime dividing n such that L squared doesn't divide n prime. Because if you prove that, then for each prime L, you can get rid of the extra copies, and then you're down to n of rho bar 3, okay? Or 3 times n of rho bar 3, because what happens at P when you're flat versus not flat is different. So let's suppose that F with Fourier coefficients A sub n of F is a cusp eigenform of type n21 over q bar 3 with n as above, and we'll let L not equal 3 be as above, so it's a prime, okay? The new form associated to F, so F is a Hecke eigenform, right? but the space of cusp forms breaks down into new forms, direct sum, old forms. And these eigenspaces, I mean, we have multiplicity 1 here, right? So there is some new form attached to F. So you can see chapter 3 where we talk about this. This certainly has level dividing n. So without loss of generality, we can assume F is a new form, okay? Then the classification of Karyolivny tells me that rho sub FL is one of the following two types. It's either a direct sum of two ramified characters alpha beta from from the local Galois group GQL to Q bar 3 star, whose reductions alpha bar and beta bar from GQL to F bar 3 star are unramified. So you're sort of ramified 3 addically, but not mod. You're unramified mod 3. Okay. Or it's an induced representation from K to GQL of psi, where K is the unique unramified quadratic extension of QL, and psi from GK to Q bar star 3 is a ramified character with unramified reduction mod 3. So very similar, but two different kinds of reductions. So we have a direct sum of ramified characters or an induced representation. And then you just kind of argue case by case. The first case produces the desired result quickly, giving us the new form F prime of type n over L to epsilon squared over Q bar 3, giving rho bar 3, where epsilon is a character that reduces to 1 mod 3. Okay. Now, rho bar 3 is not induced by the Galois group of Q adjoined root -3. So Karyol's lemma from earlier implies the result that we want. Basically, you can replace the epsilon squared by 1. So remember, the character didn't matter in Karyol's lemma under the correct assumptions. And that assumption was that rho bar 3 isn't induced by the Galois group of Q adjoined root -3. And so we're done there. So this is kind of an easy case. Case 2 is more difficult. So it again uses the fact that rho bar 3 is not induced by the Galois group of Q adjoined root -3. So here's a brief sketch. You take a prime Q not dividing 3n such that rho bar 3 of Frobenius at Q is conjugate to rho bar 3 of C, where C is complex conjugation as usual. I think you can do this basically by Chebotarev density. Our result found in Ribbit, congruence relations between modular forms, or RCR, guarantees us a new form F prime of type n prime times Q, weight 2, character 1 over Q bar 3, where n prime divides n, such that rho bar of F prime is isomorphic to rho bar 3, and such that rho bar FQ, so this kind of local representation attached to that global representation on Z hat tensor Q from earlier, has some extra special properties that I don't really want to get into. If rho F prime L is not of the second type in the Karyolivny classification above, the method of the first type in the classification then gets rid of the L squared in the level. That's what it does. And then Mazur's result actually, so Mazur's part of the proof of Ribbit's theorem from subsection 3 kills off the Q, which finishes the task. So what does this mean? The upshot is I can actually assume that rho of F prime L is in type 2 in the Karyolivny classification. Okay, so now you have to get into some weird Jacquet-Langland stuff to finish. Let's let B be the quaternion algebra over Q of discriminant PQ. By Jacquet-Langland's and known results, rho of F prime can be built from the 3-adic Tate module of the Jacobian of a Shimura curve of specified level associated to B, similar to what we did in the proof of Ribbit's theorem. A version of Karyol's lemma, which I said we were going to use, then shows that rho bar 3 itself actually arises from the quotient of this Shimura curve by the canonical action by F star sub L squared cross F star sub Q squared. And by the way, where does this random action come from? This action on Shimura curves is sort of the analog of the diamond operators on modular curves, okay? If you use Jacquet-Langland's again to switch back to modular curves, you find that rho bar 3 must be modular of type n double prime Q2 1 over Q bar 3, where n double prime divides n over L. So you need to get rid of this Q. Well, Mazur's result does that. Mazur's result's great at killing off extra auxiliary primes that we have to introduce due to technical issues. All right, so this is the end of chapter 7 of my notes. Ribbit's theorem is proven. We have minimality of the level coming from Langland's tunnel. We're all set. We're going to totally switch gears going into chapter 8 starting tomorrow. And we're going to start talking about Mazur's deformation theory of Galois representations. So I'll see you then. Thanks for watching.